Hi, everyone. Good afternoon or good morning, depending on where you are. Thank you so much for joining us today for the second webinar in our Essentials series. Today's webinar is an educational session where we'll be discussing surface energy, polymer types, and some challenging applications that you guys may see on a regular basis. Having a background in the basics of bonding will help you create better solutions for your customers and for your customers' applications. Just a few housekeeping notes. If you have any questions, we do have a chat box available, and if you submit your questions, we'll cover them at the end of the webinar. So today's Essentials series is the Essentials of Bonding, Surface Energy, Polymer Types, and Applications. So we'll get started here with just some introductions about who we are. I am Janet Page. I'm the Senior Marketing Manager responsible for industrial tape and medical products. I've been with MacTac for 19 years, the last 6 of which have been in a marketing role supporting our industrial and medical tape business. And joining me today is Steve Schroff, so I'll let Steve introduce himself.
Hi, I'm Steve Schroff. I'm the Business Development Chemist for the Industrial Tapes and Products Division. The 20 years I've been in the pressure-sensitive industry, 15 of those years has been in product development or engineering or some capacity or hybrid of both of those.
Great, and we'll just cover a little bit about MacTac. MacTac was founded in 1959. We're headquartered here in Stowe, Ohio. We are roughly a $350 million company. In 2016, we were acquired by the Lintec company. Lintec is a $2 billion pressure-sensitive company based out of Tokyo, Japan. And our location here in Stowe is actually the North American headquarters for Lintec USA. And just Lintec USA also includes, in addition to MacTac, includes Matico, who specializes in high-end window films, and VDI, specializing in metallized film products. And we'll give you just a little background on all of MacTac's products. First, we have a graphics division. Our graphics products are used in products like signage, wayfinding, fleet marking, window, wall, and floor graphics. Generally speaking, these products are designed for wide format inkjet printing. Next, we have our industrial and medical tapes division. Steve and I both represent that division. We are actually MacTac's fastest growing business. We specialize in double-coated films and foams, transfer adhesives, and custom engineered solutions for industrial and medical applications. We have a sheets division specializing in laser sheets, offset, and digital sheet products, generally used for promotional products. We have a narrow roll format division, which is designed for aqueous inkjet, UV inkjet, toner, and HP indigo printing. And finally, we have our roll label division, which is our largest business unit. Roll label specializes in pressure sensitive label materials, anything from packaging and shipping labels to UL recognized durable labels and security labeling products. So without further ado, I'm going to go ahead and pass the mic over to Steve, where he will get into some of the technical content of today's presentation.
Okay, so there's a lot of factors and idiosyncrasies that really go into it when we talk about adhesive bonding, and it's inevitable that every case is going to be different. But as Janet mentioned today, I'll be covering one of the largest factors of adhesive bonding, and that is surface energy. At one point in our careers, or in our case, daily, we've all heard or used the term LSE, or low surface energy. My goal today is really to explain this complex phenomenon in a simple, digestible, kind of fun, try to keep it lighthearted kind of format here. So first, I'm going to do a quick review. What is an adhesive? Well, an adhesive, typically they're polymers, but they're non-metallic substances used to bond two surfaces together. So we're talking about ways of joining two materials together without the use of a mechanical fastener or by any type of welding. There are two main types of adhesives, the first one being structural. Volume-wise, they are certainly the largest out there in use. And structural adhesives are basically defined as adhesives which are applied in a fluid state to wet the surface, and then they harden by either drying, cooling, or curing to form their permanent bond. And then the other adhesive we have is pressure-sensitive adhesives, which we're all here for today. These adhesives are capable of wetting a surface and forming a permanent bond with just the application of pressure. It's worth noting that paints, caulks, sealants, although these are technically not adhesives because they're traditionally not used to bond two surfaces together, unless you're like me and you let your dirty paintbrush lay on the bench top, then it's certainly stuck two surfaces together. But ideally, they're not used as adhesives. They're not sticking anything together. However, they are driven by the same principles as other adhesives, and that is, they need to be able to wet a surface to form a bond. So, and really when we're talking about forming, wetting the surface, that is the one thing all these different materials have in common. When we say wet the surface, it's the adhesive really needs to be able to flow out and make intimate contact to really down to the molecular level in order to be able to bond those two surfaces together. When we say wet the surface, it's a phrase you're going to hear, it's going to be a recurring theme today. It's a phrase you're going to hear over and over again. Now, focusing in specifically on pressure-sensitive adhesives, pressure-sensitive adhesives, or PSAs for short, they are very unique in that they are both solid and liquid at the same time, or known as viscoelastic materials. They can both flow and resist flow simultaneously. So I have here silly putty. At some point, we've all played with silly putty, or we held it. And when you hold silly putty in your hand and you're working with it, you look at this material and you're feeling it, and you're saying to yourself, well, this really isn't a liquid, this is a solid. However, if you roll it into a ball and set it on the table, come back 15 minutes later and that ball has now become a pancake. So it's still flowing. So that's the unique nature of pressure-sensitive adhesives. When we talk about pressure-sensitive adhesives, there's really three types, and that is acrylic, rubber, and then you have silicone. We won't talk much about silicone today. Everything I've discussed applies to all three types, but really 95–97% of the market is acrylic and rubber. Silicones, although highly engineered, very good, high-performing materials, they also come at a 10 to 20 times the price. So whereas you might pay 90 cents for a double-coated rubber per MSI, it's very easily $15 to $25 for a silicone. So it just gives you an idea of how expensive they are, and they're not really used unless really needed, which I'll cover here a little later in the presentation. So one of the most common questions I always get when talking to customers is they always ask, which adhesive chemistry do I select? And so I always try to answer this question the same way I approach my problem solving, which is I ask two questions. The first being, will the adhesive physically adhere to the materials or the surfaces that are being used in the application? If the adhesive won't adhere, that's pretty simple answer, and it stops there. You need to look for a different solution. And then once I answered if the adhesive will adhere, the next question always is that will the adhesive survive the environment that it's in? And when I talk about the environment, is it going to be an aqueous environment? Is there going to be a lot of chemical contact? Is there going to be a lot of heat? Or is there going to be any UV exposure? Really, at MacTac, we tend to start with rubber as our primary go-to solution. In the next several slides, I'm going to explain why this is. So really, the first part of understanding surface energy is getting into and understanding polarity. I'm sure many of you have heard the terms polar and nonpolar surfaces, or polar and nonpolar, with references to different materials, surfaces, or solvents, polar solvents, nonpolar solvents, things like that. These are terms we use a lot and might not fully understand, so I'm going to take some time to explain that. So if we first look at a rubber adhesive backbone, and right now I'm sure many of you are panicking, just wondering what these hieroglyphics I just displayed are, but I promise you, you won't need chemistry to understand what I'm going to discuss today, and there will not be a quiz at the end of this. So just kind of giving the backbone of these structures as a visual frame of reference for what I'm going to describe as polarity. So when we're looking at a rubber adhesive, I'm showing you, this is isoprene. It's a very common mid-block rubber used. If you ever heard of butyl rubber or butadiene rubbers, they look very similar, and all the concepts that I'm going to talk to applies to them as well. Now looking at the backbone here, it's pretty boring. It's really the same structure repeating itself over and over. There's a bunch of hydrogen and carbon atoms bonded together with single and double bonds. So each one of these little lines or dashes, they represent a bond. And anything that looks like a equal sign, that's what we call a double bond. And the only reason I'm bringing this up is that whenever you hear somebody ask or talk about UV resistance or lack thereof, this is the part of the actual chemistry of the adhesive that dictates whether it does or does not have chemical resistance. And I'll cover that a little bit later in the presentation. But if I put in some dividing lines here, really this polymer is pretty symmetrical. Again, not a lot going on here. And when you take into account that this polymer is not static, it's constantly rotating around, you get something that's very symmetrical. Now, if we look at an acrylic adhesive in comparison, now you're going to see something a lot different. The backbone, which connects everything together, looks a lot like a rubber adhesive, but you notice these large side groups hanging off the main chain and that they contain oxygen. And when I put in the dividing lines, even if this thing is rotating around, you're going to notice this is very asymmetrical, or not the same if you were to fold it in half. So the next part of this would be looking at charge density. When you look at charge density, polymers themselves, they form what's known as covalent bonds, which means they're sharing electrons. And carbon, they're pretty good people. They share electrons equally with all the hydrogens that they're connected to. On the polymer backbone and at the end of the groups where it's all carbon and hydrogen, there's not a lot going on. However, if you take a look at everywhere where there's an oxygen present, well, oxygens are kind of selfish and they hog electrons. And so what's the natural result of this is polarity, or you get an area of positive and negative charge, which is caused by the uneven pull or sharing of the electron. Again, oxygens tend to hog them. So this is kind of a visual representation of you get a plus charge and a negative charge, kind of like an electricity and polarity. Or quite literally, you get kind of for any Star Wars fans out there, there's an unbalance in the force. So whenever you see oxygens or nitrogens or halogens like chlorine, you get what's known as a polar molecule. Going back up, and sorry, I'm going in reverse my clicks there. Going back up and looking at the rubber-based adhesive, again, you don't see any oxygens there, any nitrogens, any chlorines, so there really is no charge density. And I'll be hitting on this and polarity. This is the definition. This is a visual representation of polarity. And as you'll see here shortly, it really does tie into surface energy.
So it might be a good idea right now just to recap a little bit for you guys. Basically, in a nutshell, as Steve explained to me earlier, polar materials are considered high surface energy materials. Non-polar materials are considered low surface energy materials, and Steve will explain why this is in the next few slides. But can non-polar materials and polar materials be adhered to each other? And they can, but there are some unique properties that come, and it does matter which material is which, or if you say it another way, is the adhesive or the surface polar or non-polar?
Summary, Jan, thanks for that. So now we're kind of getting into understanding surface energy, which really is the basis of bonding. It doesn't really matter what type of adhesive we're talking to. Everything revolves around surface energy. So now that we covered what polarity is, it's time to go down another level and really, in our quest for adhesion, and really look at surface energy, understanding surface energy, and how polarity plays into that. So I'm going to give you the definition of surface energy here, which is the excess energy at the surface of a material as compared to the bulk, which is probably really confusing. And I'm going to explain that here, and it's actually quite simple to understand, but I'm going to leave everybody with a more simplistic definition to remember, which might be more helpful, and that is surface energy is the force of molecular attraction between two materials. Another way is saying is how well the two materials going to mate up against each other and really be attracted to each other. So the basic rule of thumb in everything that we do here for adhesion, all of us chemists when we're designing stuff is and recommending products, really the basis of rule driving all adhesion is that the surface energy of the material that's being adhered to should be greater than or equal to the surface energy of the adhesive that's being used. Now, a lot of you might be wondering, well, how am I going to know if the surface energy is greater than or equal to the surface energy of the adhesive? Don't worry, we have a nice cheat sheet that we're going to hand out and send out. We'll give you an electronic version. We can send you print copies. It's a nice little cheat sheet that you can always have with. So there's really no, you don't have to memorize anything like that. So So when we talk about going back to the original definition, if we look at a material, pick any material, let's say a foam, let's say EPDM foam, and we're going to the very, very center of that foam, which is known as the bulk. In the center of that, each one of these circles then represents a molecule that's making up that EPDM foam. And each one of those molecules is interacting with each other. Now, if it's a polar molecule, we'll say like a polyester, there's a lot more interaction, a lot more attraction between those molecules, again, because you have sites of polarity, of uneven charge distribution. Non-polar surfaces, the molecules don't interact as strongly to each other, but there's still an interaction. And those arrows are just showing that every molecule's interacting with each other molecule next to it in every direction. This is at the bulk, or at the center of the material. Now, if we were to look at the very surface of the material, yeah, you see some bulk underneath, but the first thing you notice is that there's a dead space above. This is what we're talking about when we say the excess energy at the surface of the material. See, the very last molecules are the ones on the very surface. They don't have as many molecules to play with as, say, the molecules at the bulk, because there's nothing on top of them. So there's all this free energy kind of hanging around there. So now, taking another level, we're going to expand on that rule and change it around a little bit, but we're going to say for good wetting to occur, and again, wetting is really the fundamental part of adhesion. For good wetting to occur, the surface energy of the substrate must be greater or equal to the surface tension of the adhesive. So for demonstration purposes, moving on, I'm going to refer to the substrate as the surface energy of the substrate, abbreviated SDS, and I'm going to highlight that in yellow. And I'm going to refer to the adhesive as the surface tension of the adhesive. I'm going to abbreviate that STA, and it'll be in red. Now, real quick, you might have noticed I kind of changed terms around, just so everybody knows that surface energy and surface tension are really the same thing. They're measured the same way. They have the same unit of measure. For simplicity's sake in engineering, we just refer to liquids as having surface tension and solids as having surface energy. So I'm going to show a drop here. Again, with liquids, either structural, that are physically in the liquid form, or with pressure-sensitive adhesives that are viscoelastic, it's the liquid component that's involved in the wetting of the surface. So I'm going to represent here, to start, a droplet. So everyone thinks liquid at this point. And it might be a little hard to see, but this droplet is comprised or filled with a whole bunch of little circles. Those little circles represent the molecules that are making up the adhesive. And all those molecules, again, as I showed before, are interacting with each other. And the neat thing is about liquids is that surface tension, the net force of all those molecules interacting each other is that they form distinct driplets or drops. I shouldn't say driplets, it would be droplets. So whenever you have whenever you have water, you notice that when it's dripping, you see distinct droplets. Or if you're taking water and you're squirting it out of the end of a hose with no nozzle, you'll notice that the water maintains the shape of the hose for several feet and then it breaks apart. This is the act of surface tension. And what surface tension is really doing here is that it's really holding that liquid together in a distinct phase, and it forms a drop. So now what happens when we have the adhesive droplet making contact with the surface? That's kind of fun. I'll do that again. So now we get what we're going to call an adhesive bead for all intents and purposes. So now we have this bit of adhesive on the surface. It's making contact with the surface. So now all those molecules that were on the surface, again, remember they had no one to play with above them because they were at the very edge. You know, they have molecules beneath them, but there was nothing above. Well, now they have something to interact with, and what they're interacting with is the adhesive. So again, you know, the surface energy of the substrate, all that extra surface energy, how that functions is that extra energy is now pulling the adhesive that's on contact with the surface, and it's pulling it and it's trying to stretch it out. In exact opposition to this, we have the surface tension of the liquid, which is again represented in the red. So as the surface is trying to pull that adhesive and trying to get it to wet out and go along the surface of the material, you have the surface tension trying to maintain the shape of the droplet and try to pull the liquid back. And it's this balance between the two which really determines the how well an adhesive bonds. And this is really the interaction between surface energy and surface tension. So I'm going to take it a step further here. And so now we're looking at two different surfaces, and the first thing you notice is that the bead of adhesive looks different between the two. Now, just for this example, keep in mind that the same amount of liquid, we'll say fictionally we use 3 milliliters of adhesive, was applied to both surfaces. And what you notice though is you get a much different looking bead. So on the left, what this is representative of is a polar material. It's a material with a lot of polarity, as we discussed, and polarity, as we discussed before, a lot of charge there. So you got a lot of force there working on that adhesive, kind of spreading it out. On the right, though, you have something that doesn't have a lot of polarity to it, something that doesn't have a lot of net charge, kind of like we discussed before. And so the surface tension of the adhesive is really working to pull it together. So you might be wondering, well, how can I tell this without knowing what the materials are? Aside from the fact I wrote the presentation, I know the answer, but really what you notice is that if you ever see old coots like me going and visiting people, and we take like a bottle of water and we start spilling it on surfaces, or sometimes we do it for coffee, what we're actually doing is this, and we can actually tell a surface energy of a material just by putting a few droplets of water and seeing what kind of bead is forming. And we can get an idea. We can't measure it precisely down to the dime, but we get an idea if something's polar, non-polar, or hydrophobic, hydrophilic, which is another way of saying that, but we get an idea of what the surface energy is. So again, looking at the example on the left, we have the surface energy of the material pulling against the adhesive bead, the surface tension trying to hold it in. And really in this example, there's a large difference between the surface energy of the substrate versus the surface tension of the adhesive. And the result of that is you have greater flow across the surface, or you get wet out. Again, look at how low that bead is. It's covering up, or it's encompassing a larger area of that substrate. The substrate is pulling on it much harder than the surface tension is able to hold it in place. That is a high surface energy material. On the right, then, we have an example where the surface tension of the adhesive is much greater than, say, the surface energy of the material fighting it back, fighting to hold it, or I'm sorry, I'm saying this in reverse. The surface tension of the adhesive is really holding the bead together much stronger than what the surface energy of the material is trying to stretch it out. In this case, there's a much smaller difference between the surface energy of the substrate and the surface tension of the adhesive. What that results in is a lower flow across the surface, or you don't get as much wet out. And this is what we call low surface energy, or LSE for short. So we all seen a practical example of this in real life. And what I have here, a picture is a waxed car. This isn't my car. I never waxed my cars. In fact, my car gets washed once a year, whether it needs it or not. So I'm not big into the car care. But if you ever notice that after you wax your car and it gets wet, you get a lot of beads forming up. Well, the reason for that is that water is a very high surface tension material, and wax is a very low surface energy surface. And so you get, I'm just going to go back into the slide. So you get the example on the right. When you have something that has high surface tension and on a surface that has very low surface energy, you get a very highly formed distinct bead. When the car isn't waxed, sometimes you can't even tell it's wet because the water just wets all the way across say the hood, and you can't even see distinct beads. That's because the paint or the clear coat used on the car is very high surface energy, and the water wets across that as compared to the wax. There is actually a science, and the photos on the right is taken from using what's known as a goniometer, and really this is how one of the methods we can use to measure surface energy of materials. It's one of the more precise measurements. We take various liquids and then we drip them on a surface and we look at them through a microscope here on the side, and then we actually can take a measurement of that angle, and it's a way of measuring surface energy. So now looking here, we come to the cheat sheet. that I mentioned, surface energy of common materials. So this first column here, this is going to be low surface energy materials. Again, your bead is kind of sitting really high. You have what would be known as a high contact angle. That bead of adhesive just isn't flowing across the surface. Here, encompassing this, you have polyvinyl acetate, styrene, EVA, propylene, polyethylene, TPO, kind of a blend of the two, EPDM. These are all your low surface energy. And how we measure this, it's known as a dyne. You don't need to know what a dyne is, but it's a unit of measurement that can actually be tangible and quantifiable. Again, using a goniometer, we can actually determine the energy, and we use dyne to describe that. Moving over here, we have what we call the high surface energy plastics, quite a bit higher than the low surface energy materials. Kapton, nylon, polyester, epoxies, polyurethanes, ABS, polycarbonate, vinyl at the end there. All these are materials that are usually not known, hard to stick to. The materials on the far left, everybody has problems sticking to polyethylene, polypropylene. These materials here, not very hard to stick to. Though we call these the high surface energy plastics, really it's about medium surface energy, especially when compared to the metals. So as you see here on the far right, we have the metals, aluminum, stainless steel, glass, porcelain. If you were ever put a drop of water on them versus a plastic, the water just immediately wets out. It's very hard to see a drop. Again, it's because of the high surface energy. So going back to the original question that I had asked or proposed, or the statement I originally proposed, that MacTac usually starts with rubber-based adhesives. And why that is that a rubber-based adhesive, typically they all fall around 28 dynes. So rubber-based adhesives cover the largest range of materials in which they'll adhere and really wet out. They're about 28 dynes. There's not a lot of fluctuation there. An acrylic example, though, really the low end of an acrylic adhesive, the low end is about 38 dynes. Acrylics have a lot more variability. They can get as high as 45, 46 dynes, really depending what monomers are used to make up that acrylic. I won't go into a lot of detail there, and I'll use the low end, but as you can see, acrylics just don't do very well. Straight acrylics just don't do very well on the lower surface energy materials. Again, the rule of thumb is that you want your adhesive to be equal to or less than the surface you're trying to stick to. Rubber-based adhesives far below PVA, styrene, and it's really below polypropylene and equal to, polyethylene, TPO, depending on who's measuring it. It's for sitting equal to or less than. But again, the acrylic adhesive at 38 dynes, it's well above those surfaces. A straight acrylic just doesn't stick very well to them. You have to start getting into modified acrylics or LSE acrylics.
So we'll just go ahead and summarize just some of the attributes of a rubber-based adhesive. Rubber-based adhesives give you excellent low surface energy adhesion. One of the common things we like to say here at MacTac is that we're living in a plastic world, and those plastics are changing on a daily basis. As lightweighting and other technologies come into play, we are seeing people use the lower surface energy plastics more commonly in a much greater variety of applications. So having adhesives that are designed for those low surface energies is increasingly important. We also at MacTac believe that rubber-based adhesives give you the best balance of adhesion properties. What we find is that you don't have to sacrifice peel and tack to also have excellent shear strength. Oftentimes in an acrylic product, you have a trade-off between something that's highly cross-linked and exhibits high shear strength, but you may see lower peel and tack numbers, and that's just some of the basics of the polymer design itself. And rubber-based adhesives typically are the most economical solution for many applications. And we do get instantaneous adhesion with little peel build. So there may be some familiarity with some types of acrylic adhesives do take up to 24 hours to build their permanent bond strength. Rubber-based adhesives really give you that performance almost immediately. And we also find that rubber adhesives are underutilized in many applications. So there are a lot of folks who believe that acrylic adhesives are superior, and in some cases they are required. That is most certainly true. But a rubber-based adhesive can really meet, I would say 95 to 98% of the applications that we come across on a daily basis. However, rubber-based adhesives do have a few drawbacks, which we should talk about. And Steve did mention this with the double bond phenomenon earlier in his discussion about polarity. Rubber-based adhesives do exhibit some poor UV resistance over time. But that isn't to say they can't last outside as long as the adhesive itself is protected by some kind of a film or opaque material. They do have poor heat resistance. Really once you get upwards of 200 degrees Fahrenheit, that really maxes out the performance of most rubber-based adhesives. And they do have poor chemical resistance, but it is probably important to mention that they do perform well in aqueous or wet environments. They do have good resistance to polar solvents, like alcohol or MEK, but they also do not exhibit plasticizer resistance or any resistance to organic solvents or fluids, things like heptane, toluene, gasoline, and oils. When we talk about acrylic adhesives have very good UV resistance, and they are cross-linked polymers, just as 100% solids acrylics are similar to solvent-based products. They have excellent UV resistance, excellent temperature resistance, and very good chemical resistance, really pretty much across the board. And they give you a good combination of all of the properties that you're looking for, peel, tack, and shear. And they also exhibit low VOC and migratory properties. So they have very little outgassing or migration because there's no retained solvents or residual monomers in 100% solids acrylic adhesives. And we also find that the coating process is actually more cost effective. And Steve will take it away with applications and adhesive selections.
Yep, so we kind of showed you what polarity is, what surface energy is. Now we're just going to go through some practical applications that we've gone through, how each of those fall into these practical applications, and just the idea that was used. Oops, sorry, I had to unmute myself. That goes into the adhesive selection that we use. So first one we see a lot is trying to stick to a cross-linked polyethylene foam. Some of the Zote foams that are out there, Voltec, a lot of polyethylene foams used out there. When you look at a polyethylene, backbone-wise, polyethylene looks a lot like a rubber material. In fact, even for an experienced chemist like me, if I don't know what the materials are and I just see a formula, I really have to concentrate to determine because they're very hard to tell apart. So polyethylene is a LSE material. So one thing that sticks very well to LSE materials, of course, are rubber-based adhesives. The nice thing about polyethylene polyethylene foams is that they have very poor temperature resistance for foams. So you can, rubber-based adhesives stick very well to them. One of the drawbacks to rubber-based adhesive is that they have poor temperature resistance. However, the cross-linked polyethylene foam itself has poor temperature resistance. So, rubber can typically be used there. You don't have to worry about it. If you're using a polyethylene foam, however, and you need chemical resistance, well, depending what the chemicals are, you might need an acrylic. Straight acrylics do have trouble sticking to polyethylene foam. You have to then get into modified acrylics and start looking at more specialty products like that. Polyurethane foam, on the other hand, is a higher surface energy than polyethylene foams. However, they are typically used in higher temperature applications. So again, with the higher temperature, you're going to want to use an acrylic. The nice thing is that the higher temperature the higher temperature of the polyurethane, much higher than the polyethylene, but they have higher surface energy than the polyethylene. So acrylics work out very well here. I will mention one little factor here that does tend to trip people up, and that is that because polyurethane is easy to stick to and has high surface energy, polyurethane itself tends to like to stick to itself. And what would happen is that if you have a straight roll polyurethane foam, that doesn't have any anti-block on it, it tends to form a giant solid mass. So companies out there, Rogers does it a lot, Burnett, They put what's known as anti-block additives onto the polyurethane, and what that does is it keeps the urethane from sticking to itself, so that when you go to unroll it, you can actually get it apart, or if you stack converted parts on top of each other, that those parts actually come together. Because if you didn't have that on there with certain formulations especially, they tend to stick to themselves and they all lock up and form a solid mass. The problem with anti-block is that it keeps the foam from sticking to itself, but it can also make it hard for an adhesive to stick to it. So sometimes you need a rubber to be able to stick to those because of the anti-block additive that's put onto or into the polyurethane formulation. Another application we see a lot of is bonding abrasive to foams for cleaning pads. Because this is an application where cost is pretty critical, you want to keep the product as cheap as possible. So we gravitate towards rubber because they're the most economical solution. The reason why rubbers work here, again, one part is, will it physically stick? These materials, yeah, even acrylic would stick to a lot of these materials. Will it withstand the environment? Again, rubber is not great chemical resistance, but rubbers do really well in aqueous environments. And this is a difference because of the polarities, water being very polar, rubber being very non-polar. Even with detergents in there, rubbers will withstand water and aqueous environments just fine. So this is a case where we go to a rubber. Again, some of those idiosyncrasies of what adhesive do you select, cost always comes in there at some point. This application is always rubber because it needs to be cheap. So let's take a look at another aqueous environment, which would be gasketing material used in marine bilge or around the bilge pumps. So this is an aqueous environment. However, when you look at a lot of what you find in bilge areas of a boat, you find a lot of oil, you find a lot of gas, you find a lot of diesel fuels. These are things that are very detrimental to a rubber. So in these type of materials, cost isn't necessarily as important as, say, a disposable cleaning pad. And that's good because rubbers might not do well here because of all the organic materials floating around there. They're going to get in there, they're going to dissolve, they're going to plasticize the rubber, and it's going to break down. In this case, in this aqueous environment, we would use an acrylic adhesive. Roofing membranes. Roofing membranes plays into the surface energy. A lot of your roofing membranes and roofing underlayments for shingles are TPO materials. Again, TPO is typically a blend of polyethylene and polypropylene, very low surface energy materials, very hard to stick to. Rubbers stick really well to those. When you look at then what that roofing membrane that's coated with a rubber-based adhesive or an adhesive, it's got to stick to the wood decking underneath. And so that MDO tends to be very textured. So when sticking to that, you want to use a very heavy coat weight of adhesive, and rubbers are just better at being able to coat thicker. And the reason why is that if you're talking solvent acrylic, you got to dry the adhesive. And if you're talking UV acrylic, although we can get much thicker in our UV acrylic coat weights, you still have to be able to cure through them. With rubber and hot melt processing, really all they do is cool. So as much as you can pump and lay down is as much as you can coat. So really the sky's the limit. For some of our GS products, we coat up to 50 mils thick. So in roofing membranes, we go directly to rubber, mainly because the membranes themselves and the underlayments are very low in surface energy. And it requires a heavy coat weight to stick to the MDO board that's underneath. I'm sorry, the OSB board that's underneath. Again, some of the misconception here is that rubber products can't be used outdoors. That's not true. Rubbers do have very poor UV resistance. That goes back to that backbone and all those double bonds. However, in terms of roofing and a lot of applications, outdoor does not equal UV exposure. The adhesive itself has to have direct line of sight to the UV source, in this case the sun, in order to be broken down. With roofing membranes, it's buried underneath the roof. It's never going to see the sunlight. There is no direct UV exposure. In these cases, we use rubber 100 out of 100 times. Camera heaters are assemblies on automotive parts. So as we get to more autonomous vehicles, more smart cruise control, more lane departure warnings, these all have cameras. I think I saw the GMC trucks have 15 different cameras on them. Well, for those cameras to work properly, they have to be seen. And we all heard of the Tesla autonomous vehicle crashing. Well, what they found is that as the window fogs up or starts to ice up, you turn on your defroster, but the cameras sit up behind the rearview mirror at the very top, so they get defrosted or defogged at last. So what everyone's starting to do with their cameras is that they're putting printed circuits that are heaters, and they go around the camera, and so the camera has its dedicated own defroster that's always running. Well, in this case, because it's on a windshield, which is glass, there is extreme UV exposure. So we would never ever recommend a rubber-based adhesive for this. It wouldn't last more than 6 months. Also, there's very high temperatures here, not because of the interior of the car, but because that printed circuit can get up to several hundred degrees to keep that area around the camera defrosted and de-iced. So in this case, not a lot here. Surface energies, glass is really easy to stick to, but it's more the environment with the UV exposure and the high temperatures. So that concludes our presentation. We'll take questions now. I don't know, Janet, if you've seen any questions that have come in.
Yep, we do have a few questions, Steve. So we'll go ahead and we'll go ahead and get started on those. So the first question we have is, what are LSE acrylics and which is better on an LSE surface, an LSE acrylic or a rubber-based adhesive?
Okay, so I mentioned LSE acrylics. I didn't want to get too in depth there because it would take us down a rabbit hole, but LSE acrylics have tackifier added to them. And the idea behind the tackifier is really you're trying to make the acrylic look like a rubber, because the rubber has a lot of tackifier. And so the tackifier gets put in there and it lowers the surface tension of the acrylic adhesive, and it helps it wet out across low surface energy materials. I think the second half would be, is it ever as good as a rubber-based adhesive? And the answer there would be no. A rubber-based adhesive is always going to be better on low surface energy materials than even an LSE acrylic. The reason why is that the tackifiers have to be compatible with the adhesive, and the tackifiers that are compatible with acrylic adhesives are higher surface energy tackifiers. So the tackifier itself would actually be of a higher surface energy than the actual rubber, than the rubber polymer itself. So to put this in numerical terms, let's say with a rubber-based adhesive, you can get 10, 12 pounds off of a polyethylene and HDPE panel, no problem. With a straight acrylic, you might get a pound if you're lucky, maybe a pound and a half. With an LSE acrylic, you get 3 or 4 pounds. Obviously, the LSE acrylics are better than the straight acrylics, but they'll never be as good as a true rubber adhesive. Hopefully that answers the question for the user.
Yep, I think so. That was good. So the second question we have is, you showed EPDM as a low surface energy material, but I know acrylics are sometimes used to adhere to them. So why do the acrylics work, occasionally work better or as well as the rubbers?
That's a good question. This is part of the idiosyncrasies of everything that's involved. So there has got to be 10,000 different formulas of EPDM. And what we find is that if you were to use a raw EPDM foam or a raw EPDM rubber, it's very hard to stick to, and only rubber-based adhesives will stick to that. Why acrylics work is that very rarely do you ever find a EPDM foam or rubber that's strictly EPDM. What you find is they put a lot of fillers in there, a lot of colorants, a lot of fillers, a lot of other components go in there. And it's those components that are actually much higher in surface energy that changes the overall surface energy of that system. And that's what allows acrylics to actually stick to those. So in our portfolio, we recommend acrylic or rubber, but we always add the caveat, it depends on the formulation, because there are so many different types that it's hard to say definitively one way or another that one type of adhesive will stick versus another. It really depends on the formulation, and really it comes down to what are the additives that are in there.
Okay. The next question is, are all acrylic adhesives the same with regard to UV resistance?
No, there are certainly acrylics that are better. As a whole, acrylics are better than rubbers by far. However, when you look at acrylics, I won't get into too much detail here, but it depends on what monomers you're using to make up the acrylic and the type of acrylic. The easiest example of this would be emulsion acrylics will never be as good as solvent acrylics. Although they're both acrylics, emulsion acrylics have a lot of other additives in there. They've got surfactants, they got defoamers, they got wetting agents. And over time, those tend to yellow. Solvent acrylics don't have those, so typically if you're going for like a graphic over laminate or something that's going to be in direct sunlight, you certainly want to go with a solvent acrylic. Now, in the world of solvent acrylics, there are certainly ones that are better than others. I won't go into that amount of detail. You just need to work with us to find out which adhesive would be best.
Okay. And then how do you raise the surface energy of a material?
If you're talking about the substrate that you're adhering to, they can be changed. So, like if you have a polyethylene or a polypropylene material, those are commonly run through like a corona treater, or more modern day methods would be a flame treater or a plasma treater. And so you can change the surface energy. You could take a low surface energy material and raise its surface energy to help acrylics especially stick to them. And as I showed in the polarity slide, as you start adding oxygens onto the surface, or as you start adding oxygens into the system, you increase polarity. All those methods I mentioned work the same way in that they react with the air in the atmosphere, and they react oxygen onto the surface of your material. And because of that oxygen, it creates polarity, it raises the surface energy, and it helps the adhesive wet out across that surface and make contact. So yes, you can increase the surface energy of a material, and it can be done through corona treatment, or what's the best would be plasma or flame treatment.
Okay. Our next two questions actually I think might be related. So the first is isoprene rubber cross-linked because of the double bonds? And then the second part of what I think is the same question is, if it is cross-linked, does it lose some of its adhesive properties?
So natural isoprene goes through what Mr. Spock would call vulcanization. And vulcanization is literally cross-linking of rubber. So the isoprene I showed is polyisoprene, and those double bonds exist, and they are not cross-linked. You can cross-link to them, but they're not cross-linked. So, and where this might get confusing is that the difference between natural rubber and synthetic rubbers. In natural rubbers, you do cross-link them because natural rubber is a gummy, soft material. Think almost maple syrup. So that doesn't make a good adhesive. So you got to firm that up somehow. And so you do put some sulfur in there, and you do what's known as vulcanization, and you do cross-link to those sites. In synthetic rubbers, though, those double bonds do exist. They are still there. However, instead of cross-linking, the end blocks of those are polystyrene. Now, again, I showed the rubber min block because that's what's used, and that's the part of the rubber that does the adhesion. The styrene, though, is there as the reinforcing agent. And so why you get the best balance of properties with rubber-based adhesives is because they're not cross-linked. They just simply have massive amounts of molecular weight. And all those styrene, so styrene and isoprene, or styrene and butadiene, are highly incompatible. And what happens is that when you melt them, they're all molten and everything's flowing. But as they solidify and cool, they segregate themselves. And all the styrenes conglomerate in one area, and then you get all the isoprenes in another area, and then you get styrenes in another area. And because the styrenes are big and bulky and there's a lot of them, they act as cross links. So it's kind of a long answer. I'm trying to answer both of those. But because you have so much double bond left, when they're exposed to excess heat or excess UV, those double bonds actually break apart, react with oxygen, and they start yellowing.
Gotcha.
I hope that answers the question for the user. One thing I would say is that they did ask, if you cross-link the isoprene, does it affect adhesion? The answer is yes. But again, that only works for natural adhesion, natural rubbers. So you can cross-link butadiene and actually get you can cross-link isoprene and actually get a really hard rubber, and that's what they used to make tires out of. But again, with modern day adhesives, most of us are now using synthetic components, and you don't actually cross-link those.
Okay, so the next question is, if surface energy of a solid is greater than the surface tension of adhesive, could molten polyethylene bond a thermoset polyester?
Well, now you're starting to get into molten and welding. And so this is more like structural adhesives, and these actually perform, instead of being more like pressure sensitive, there is a component, and again, I didn't want to get into too much detail, but I'll cover this. Structural adhesives, they rely on surface energy, but structural adhesives also have the benefit of relying on something known as mechanical interlock. And that is that when a structural adhesive is a pure liquid, Isocyanate is a great, or I'm sorry, isocyanate is super glue. This is a great example because it's very fluid. It can actually soak into areas on the surface. So super glue has trouble sticking to very smooth surfaces, especially very smooth plastics, but anything that's porous, super glue sticks really well to. And that's because you get to what's known as mechanical interlocking. And so when you're talking two materials and you're talking them both being molten, they can actually kind of intermingle, and then when they solidify, they might be locked together via what's known as mechanical interlocking, as opposed to actual chemical interaction. So a lot of times when they heat weld or ultrasonically bond some of these materials together that have very dissimilar surface energies, they try and disrupt the surface, and you can actually see crimp marks in them. And the reason they do that is to create areas of mechanical interlock, because as a straight adhesive, those two are very different in surface energies, and they don't really want to bond because one isn't a true PSA. So you rely more on mechanical interlocking there.
Okay. All right. The next question is, how are cross-linked acrylic adhesives activated?
Most of the way. So if you're talking cross-linked, again, the way we do it is, and we exit solvent, we do it through UV. How it was done before that was, the most common is what's known as self-cross-linking adhesives. And how that works is you have a reactor group, you have the acrylic acid in the backbone, and in that acrylic polymer I showed, acrylic acid was sitting there. And then you have this metal chelating agent, which has a very hot positive charge. And the reason why they don't gel in solvent form is because the solvent's there and the solvent's kind of blocking those two sites from seeing each other. What happens in self-cross-linking adhesives, though, is as you run them through a dryer and as the solvent's evaporating, there's no longer anything blocking those sites from seeing each other, and those sites come together and then they cross-link. Another way of doing it is actually putting in an external cross-linker, like an isocyanate or something. Although I will say those will gel in solvent form, and I've made a 500-gallon Jello mold in the past because we did not coat the adhesive in time. So it is two different methods. And then what we did then is, that was the old method. In the early days, 30, 40 years ago, there was no self-cross-linking adhesives. You had to add them in separately. You would add, say, an isocyanate, and it would react with an acrylic acid on one polymer backbone, and it would react with acrylic acid or hydroxyethyl acrylate, which is also in that polymer backbone I showed, on the other polymer, on the other adhesive chain, and that's how it would cross-link. And then they made cross-linking adhesives where you don't have to add anything; it's already in there, and they're stable because the solvent kind of blocks the sites. And then what we did on our end is that you take out all those thermally initiated sites that require the solvent to be blown off, and you put UV initiated sites. And the only way to get those reactive is UV energy. And then once you hit them with UV energy, they become reactive. Those sites find each other, and that's how they cross-link. So it just depends which method of acrylic you're talking about.
Okay. And the last question we have is, when you refer to rubber adhesives, are you referring to butylene, isoprene, and other types of rubbers? For example, a family of elastomeric polymers.
Yeah, they all are basically, they all look the same. They're all hydrocarbon. Again, like I said, they all follow the same principles. They're all low surface energy materials. It's all a whole bunch of carbons and a whole bunch of hydrogens. And again, because carbons share their electrons very evenly, you don't get a lot of polarity there. So they all interact about the same. Really, the difference there is that isoprene, you have a methyl group hanging off of one butyl. You have a butyl group hanging off the main chain. But again, they're all hydrocarbon based. They're all carbon and hydrogen repeating, all the same. The real difference becomes when you start adding in acrylics or even polyurethanes. You start putting oxygen into the backbone. You start putting nitrogen in the backbone. And when you start putting those type of molecules, the molecules that don't play nice and don't share very well, then you start to get polarity. So your butyl, your butadiene, your isoprene, your sebs, your Sib star, all those are going to be the same basis, very nonpolar, all carbon, hydrogen, not a lot of polarity there. Hopefully I answered that one too.
Great. Well, that's it for our questions. So I'd like to thank everybody for attending today. And as a thank you for attending, you will be receiving our Essentials of Surface Energy cheat sheet. And if there are any other questions that you have either for Steve or myself, feel free to reach out to us anytime or reach out to your sales rep, and we'd be happy to talk about your application requirements with you. So thanks again, and we've enjoyed having you here today for this presentation.
Yep, thank you.